So the recording has started, so we can start now. Yesterday I have told you that you should be very comfortable with these terms, mainly the normal stress. Okay, this normal stress, this shear stress, and the stress, the sigma. Sigma in the direction of vertical, and sigma and normal, and the shear stress parallel to the plane. So this you have to be comfortable. Now let us go to the further steps of the analysis. So I will take a new screen. So I'll write it a bit properly. Okay. So gamma in the normal direction is sigma in the normal direction is was it? Sorry, sigma is normally gamma z cos beta. Sigma n will be gamma z cos square beta, and tau will be gamma z cos beta sin beta. At any point you have any doubt, please don't hesitate to ask. Okay, so now these values are the disturbing forces, are the disturbing forces, and the force that is actually doing the main damage is the shear. Okay, it is the doing the main damage. So this is what the disturbing shear force. Shear force. Okay, which is mainly doing the damage. Okay, so or we can say disturbing shear force is same as the applied shear force. That is the load that is being applied here. There is no other load which is present. So disturbing shear force, applied shear force, same thing. Okay, so it is same. Okay, disturbing shear force, applied shear force, same thing. Now there is one area of geotechnical engineering which deals with shear strength. There is one area which deals with shear strength, and when you study this area of shear strength, uh, this is generally taught in the higher levels. Okay, not right now. It's generally taught after this subject is completed. Then in-depth analysis of shear strength and all is done. But I am hoping to teach you this topic in this semester itself because we have time. So after this stability of slopes is over, I will try to discuss some higher level topics with you, like bearing capacity, shear strength, something, all those things. Okay, in details, as much as I can. Okay, in the time that is provided. So now for shear strength, there is one basic formula that is present. So that formula is shear is equal to C plus sigma 10 phi. Uh, have you did you get this formula previously? Type Y or N. Did you get this formula previously? Type Y or N. Shear is equal to C plus sigma 10 phi. Did you get this formula previously? Okay. Okay, fine. Okay, fine. So basically, this means that in a cohesive soil, Okay, if there is a cohesive soil, let me just go to it. In a cohesive soil, there is a value of C which is equal to cohesion. The force of cohesion between the particles. So represents the cohesion, and sigma represents the normal stress. Okay, sigma represents the normal stress, and phi represents the angle of internal friction. Angle of internal friction. So if there is some shear in a soil, then the shear is equal to the cohesion of the soil plus this normal stress into 10 phi. Okay, so that is the relation. Please remember it. Okay, please remember, very important relation. That is the basis of the study of shear strength. This relation is the basis of the study of shear strength. Everything in shear strength comes from this relation. Everything that you will study, you will start from here. Everything that you study related to shear, you start from here. So, if there is a cohesionless soil, okay, if there is a cohesionless soil like sand, then there is no value of C. C is equal to 0 because there is no cohesion in sand. Okay, so in that case, it will be tau is equal to sigma 10 phi simply. Okay, so like that. But in clay, there is a value of C. Okay, so if there is a value of C in clay due to cohesion, then there is a value of C that is added. Okay, so this depends on the soil, various type of soil, and depending on the type of soil, the equation changes. Okay, so please remember this. Okay, try to like memorize it, remember it by heart. Okay, so now in our case, let us consider a cohesionless soil. Let us consider a cohesionless soil. Let us, because we are doing analysis of infinite slopes at first, isn't it? Right now we are doing infinite slopes. We have done the finite slopes. So infinite slopes, let us consider the first analysis for cohesionless soil. There. Cohesionless soil. So in that case, we will get tau is equal to sigma 10 phi. And in this case, we will not write sigma 10 phi directly. In case of cohesionless soil, we will modify it and we'll write sigma bar 10 phi dash, because these are related to the effective stress parameters. In case of cohesionless soil, we write like this, because in cohesionless soil, we write in terms of effective stress parameters. Why I am telling you? It is because if you take a sample of sand and there is water in the sand, and if you apply a load, okay, so if this load is sigma, then the water will move out instantly. From sand, water will move out. It will not spare any time, directly move out. So we know that sigma is equal to sigma bar plus u. So if there is no u, because water has moved out, nothing left, so u is 0. So ultimately sigma is equal to sigma r. That means stress becomes equal to effective stress. So that's why in case of cohesionless soil, we always take in terms of effective stress. No water gone, so effective stress remains. Now, when we take up effective stress, we generally denote the angle of internal friction is equal to phi dash when we deal with effective stress. Okay, so that's why the equation becomes this one. Okay, and in our situation, what is this normal stress in our situation? This normal stress, what is in our situation? It is sigma n, isn't it? Sigma n. If you look into your diagram, sigma n. So we can also write sigma n. Okay. So are you like have you understood this equation till now? How we have got it? Type Y or C, whatever you want. I will wait until I get at least 20 Y or C's. I want to see. Okay, thank you. So now, in limiting equilibrium condition, okay, in limiting equilibrium condition, what will happen? We have already discussed that when we analyze anything, we analyze it in the equilibrium condition, okay, where the applied force is equal to the uh, capacity. Okay, just a minute. There is a call from the department. Just give me a second. Sorry for that. Am I audible? And can you see the screen? Okay. So let's start. So in a limiting equilibrium condition, shear stress is equal to shear strength. Applied force is equal to the capacity. Now, what is the shear stress that is applied in this sample not sample actually, in this slope that we are analyzing? The shear stress is gamma z cos beta sin beta. And we have already got the equation of the shear strength right now. Right now we have got the equation. So it will be sigma n tan phi dash. Sorry, not beta, tan phi dash. So let's simplify it. In place of sigma n, we can write so gamma z will get cancelled. So cos square beta and this will get cancelled. So we can write sin beta by cos beta is equal to tan phi dash. This implies tan beta is equal to tan phi dash. I hope there is no confusion with this with this solution. Simple solution we have done. So 10 beta equal to 10 phi dash we have got. This is for the equilibrium condition. Okay. So now from here 10 beta is equal to 10 phi dash. Beta was what? If this was the slope, this is the beta. So when there is limiting equilibrium, beta is ultimately we get beta is equal to phi dash. In the limiting equilibrium, beta is equal to phi dash. So when the equilibrium, there is limiting equilibrium, the slope of the angle of the slope is equal to the angle of internal friction. Okay, and now from here, if beta becomes greater than phi dash, then what will happen? Then there will be failure. That means the maximum value of beta, the maximum angle for the slope cannot cross the angle of internal friction. Okay, maximum value of the angle of the slope cannot exceed the angle of internal friction, because then it will fail. Okay, so if we just think of the capacity, if like beta, suppose phi is 35 degree, and beta is angle of the slope is suppose 24 degree, then there is stability. Okay, and there will be some like this is related to the stress term and this is related to the strength term. Okay, because 35 is coming from here, isn't it? So this is related to this right side value is related to the strength term, and this left side value is related to the stress term. Okay, the applied stress term. So now if the value is 24, then out of this strength of 35 degree, it will mobilize only 24 degree of its capacity. Mobilization concept, if you remember, if you have a capacity of taking 100 kg load, if someone is giving you 50 kg to pick up, you will utilize only 50 kg of your strength out of your 100 kg. So that's the thing. So this phi dash 35 degree is the full capacity. Okay, but applied is 24. So it will, this phi dash 35 degree will mobilize only 24 degree of its strength. So this becomes what? This becomes the mobilized phi dash. Mobilized phi dash. It will not utilize its all 35 degree strength. It will mobilize only 24 degree of its strength. Okay, so it will not utilize its full capacity. Phi dash will not utilize its full capacity. Okay, and we can also say that the total capacity of phi dash is not mobilized. It is mobilizing only 24 degree. Okay, the total capacity is not mobilized, mobilizing only 24 degrees. So you can write one line: if beta is less than phi dash, then maximum angle of internal friction is not mobilized. Just from the example, I think you can see it clearly. 35 degree applied is 24. It is mobilizing only 24. It is not mobilizing its whole 35 degree strength. So that is this thing, and in that case, this is safe. This condition is safe. but this condition is dangerous. Now, what will be the factor of safety now? Factor of safety is full capacity by mobilized fellow. Okay, so full capacity is what? In this case, it will be phi dash, and mobilized will be phi dash m. Means what? If this is the slope, okay, this is suppose 24, okay, presently, and phi dash is 35 degree. This means what? The slope can get inclined up to 35 degree. That is its capacity. The slope can get inclined up to 35 degree and it will not fail. So that this value up to 35 degree phi dash, this is an example, is the capacity. So the capacity we write in the numerator, and right now if suppose 24 degree is there, then mobilized value is obviously the present value 24. So this is the mobilized value. So capacity by mobilized value, that is the factor of safety. So this is the factor of safety. Okay, or we can also write the mobilized value is nothing but beta, isn't it? So 10 phi dash by 10 beta. Okay, so that is the thing. So I hope you have understood this part till now, and if you have any doubt, you can ask. Please, I can wait for 1 or 2 minutes. If you have any doubt, you can let me know. Okay. So let's proceed. Now, if there is a water table, what will happen? If there is water table, what will happen? Suppose this is the slope. Suppose the water table is like this. Suppose the depth is Z, same way, the depth is Z. In the previous situation, we did not talk about any water table. So right now, let us take the situation of a water table. Okay, so like this. So in that case, the applied force is same. Tau is equal to gamma Z cos beta sin beta. But the normal stress, the strength will be a little bit affected. Okay, this is the applied value. But in the strength will be affected here because ultimately for analysis we have to equate the equilibrium condition. Stress is equal to strength. So stress value will be same. Strength will be a little bit different because of the water. Because in this sample there is water present. So the water will reduce the stress. And earlier it was how much? Earlier the strength was, we have already got, the strength was, shear strength is equal to sigma n cos square, sorry, sigma n tan phi, tan phi. So in that case, this sigma n will get affected. So earlier the sigma n was how much? Gamma z cos square beta tan phi. But now this gamma z will not be just the one present. This water is there. This water is there. So water will try to reduce it, and it will be reduced by gamma z minus unit weight of water into height of water. So this water will try to reduce the strength. See, unit weight of earlier we used to take unit weight of soil into the depth of the soil. Now we are simply subtracting the unit weight of water into depth of water from it, and this is because we reduce it, the strength get reduced. Okay, so for you all, what I want to do is try to find out the factor of safety by equating the shear stress by shear strength now. Okay, we will discuss this. It is not so tough. I will complete it in the next class. Till now, till then, what you do is you equate these two terms, shear stress and shear strength. Okay, for the equilibrium condition, and try to simplify the equation for factor of safety. How, see where you can arrive. Okay, one on one side there will be uh, okay, I will not tell you, just see, like when you simplify it, where do you arrive? When you are simplifying it, where do you arrive? I will give you one hint. Obviously I will solve it in the next class, but hint is that try to bring in the term of submerged unit weight. Submerged is what? The unit weight minus unit weight of water. Okay, that will be the submerged unit weight. So try to bring this term and try to just equate this and this and see where do you arrive at. Okay, so that is just practice for you all. Okay, and okay, let's meet in the next class then. Thank you for your time and patience.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir.